This is Dr. Brothers, and this video is going to examine Barker codes and matched filtering for using the 802.11 example. So, a Barker code is a very specific code which has an autocorrelation function that results in very low side lobes. There are other types. Barker code is a specific example, but there are entire books of these codes that have low side lobe autocorrelation. They're used specifically for communications applications and a whole variety of reasons that you need these codes. So you can see here we have some Barker codes at a length 7. It gives a side lobe ratio of negative 16.9 decibels. So that's the distance from the peak down to the side lobe. If all it is correlating, it's the autocorrelation, so it's looking at itself. We're actually going to correlate this or match filter this with some random data that we're going to generate. The random data is going to come from MATLAB, so it's not going to have quite as good autocorrelation. So if we look at the MATLAB code, I'm going to start off by creating a header block that contains some comments. Then I'm going to clear the workspace. Set up some variables. So the first variable is the number of data words in my data stream. I picked 10 arbitrarily. Each data word is going to have 256 bits of data. Again, that's an arbitrary number that I selected. Then I have 3 Barker code sequences, a Barker 7, a Barker 11, and a Barker 13. And I'm going to show how each one of those operate. The next line is creating the reference signal. This flips the cyclic prefix code, and that is the step for a real signal to create a matched filter. So if it is a complex signal, you need to flip it and complex conjugate. If it is a real signal, all you have to do is flip it. The next line is the creation of the transmitted signal, which is a concatenation between the cyclic prefix and a random set of data of linked data bits. This section is creating the entire data stream, which is concatenating that transmit signal with another cyclic prefix and more random data. This is done data words time. There's 10 data words. The channel that we're going to use is a lossless zero delay channel. So it is an ideal communication channel. This line is the matched filtering. So we're looking for the start of packet indicator, which is obtained by convolving the reference signal with the received signal. So this is a convolution filter that is set for a matched filter reference. We're going to convert the start of packet into decibels. This will make it easier to see on the display. And then we're going to plot the output. So let's see what it looks like for a Barker 7. The start of packet is clearly visible in a periodic sequence through the data stream. The distance from the peak to the average, let's pull this one. This looks like he's about the average side lobe. There are some that are higher, some that are lower. But we can see we've got about 3 decibels of separation between our random noise and the start of packet. 3 decibels, if you convert that into voltage space, is double the voltage. That's a very good degree of separation. We can easily pick that out as the start of packet. But let's see what happens as we increase the cyclic prefix from a Barker 7, which is a 7-bit long code, to a Barker 11. So we add 4 bits of data to the cyclic prefix. When we run that, we now obtain a signal where, and I'm going to say this guy looks about like the average. So the difference now, we can see it is about 4, maybe 4.5 decibels from the noise. So we gained more isolation by increasing that Barker code. The last one, let's look at the Barker 13. Oops. Now we can really start to see the difference. And if we grab this and grab this one, it looks about like the average. You know, this is 8 decibels. If we look at this guy, which looks a little bit higher, this guy looks like about 5 or 6 decibels, 5.5. So we very quickly start to gain isolation. If this signal were coming into our system and we use the automatic gain control to normalize it so that we know where we should expect to see these peaks, we could set a threshold detector just below these peaks, because you can see they are very consistent in the height. They will always correlate up to the same value. So if we can get rid of the frequency shifting and we can normalize the incoming signal, we can have a very dependable indicator of our start of packet. So one last thing I wanted to show was how to publish something in MATLAB. So if you go to the Publish tab, and it might be different depending on your version of MATLAB, but it's in there. And then Edit Publish Options. Make sure that the output is set to PDF. And then if you just click Publish, it will create a very nice output, including all your comments and your section header information. This is the format that I'm expecting to see these things turned in on homework. Okay, I will post the M file and the PDF file to T-Square account. Thank you.